Hi, everybody. So I want to get started right away because we have quite a bit to practice today. I'm going to go over what we did not get to on the worksheets that were uploaded. And then I'm also going to do a little bit more. There's been some questions with some of the counting and probabilities with that. So I'm going to try to do 2 examples with that towards the end. So let's get started. I'm going to share my screen and we will start with the worksheet that has the cards on it. We'll start with that. We did not get to the pregnancy test results example on the last meeting. So that's where I want to start here. Okay, so what you see on your screen is the pregnancy test results. And when we started the Zoom meeting yesterday, we were looking at students who listen to music while they're studying or not. And it was male, female, and then the category listen to music or not listen to music. So that was the 2x2 contingency table. This is another example of that. And I have already written the totals, the column and the row totals to help you get started. But when you see the contingency table, usually we don't have the total rows, the total row, and the total column. We just see the information in the body of the table. So it's our job to interpret this. So I'm going to go ahead and fill in these totals. So just add down each column and then add across each row. And then when you add down the column and the row, you should get the same number of 99 in that bottom corner. Okay, so let's look through these and let's answer these questions. What is the probability of a woman being pregnant if the test indicates a negative result? Okay, so we want to write this with a restriction. So what I mean by that is I want to look at the probability that the woman is pregnant given, so there's a bar, given that it's a negative test result. So I'm using that notation and I'm going to isolate the category that I'm taking the probability from. So the negative test results, the number of people, a number of women who got a negative test result, there's 16 total. So I know that that is out of 16 because I am restricting it to that category. The total number of, given that the women had a negative test result, so that's out of 16. Out of those 16, how many were actually pregnant? And we see up here that 5 are pregnant. So I know my probability is 5/16. I'm not going to worry about getting the decimal for these. I'm just going to go through how to get the answer. So my stat lab will tell you how many decimals to round to, or else leave it in a simplified fraction. All right, let's move on now. What is the probability of a false positive, which is the probability of getting a positive? So we want, what is the probability of a positive test result given that the woman is not pregnant? So again, that bar that I'm writing is indicating given out of the number of women who are not pregnant. So when I do that, I'm going to look at the number of women who are not pregnant. There's 14 total. So I know out of my 14, out of the number of women who are not pregnant, out of 14 of them, how many got a positive test result? And we can see that 3 got a positive test result. So let's now explore this idea, which is called confusion of the inverse. So as I look at part 1 and part 2, part 1 is the probability of being pregnant given that there's a positive test result. So if I flip the order of that, that's number 2. What's the probability of a positive test result given that the woman is pregnant? So are these the same probabilities? That's what we're exploring. So let's first start with the probability. Let's start with part 1. Probability that the woman is pregnant given a positive test result. So let's go back up to our table, and I want to take it out of the total number of the positive test result. So as you're looking at your table, the total number of positive test result is 83. So I know that is what I'm taking my probability out of. And then we want to know how many were pregnant. And I see that 80 were pregnant. Okay, let's look at now part 2. Now we are looking at what is the probability of a positive test result given that the woman is pregnant. So I need to go to the total of women pregnant, which is 85. And I want to know how many of those have a positive test result. 80 have a positive test result. So my numerator is 80. So do you see that these are not the same? The denominator is not the same. So you need to be really careful on where category you're designating. So what is given? Given that it's a positive test result, then we have to go out of the total number of positive test results. Given that the woman was pregnant, then we want to go take it out of the number of women who were pregnant. Okay, so make sure you're exploring those ideas. That's the last of that worksheet. We didn't get to all the way through it. We did the cards example on it. We did the carabiners yesterday, and this was the 3rd problem on that worksheet. So now let's shift gears and let's go into, move this up here. Let's go into the 2nd worksheet. Okay, so we on the 2nd worksheet, the first one was with the students listening to music while they're studying. The 2nd one was the driver's license. The 3rd one was the dogs and the cats with the households. The 4th one was the marbles. So we've done all of those 4. We've done the first 4. So we're going to start on number 5. Move this down here so I can write better. So number 5 on that worksheet says individual plays on a slot machine are independent. Okay, so that means that if I pull the slot machine, that's not going to affect the next time I pull the slot machine. So individual plays are independent. The probability of winning on any play is 0.38. So the probability of winning is 0.38. What is the probability of winning 3 plays in a row? So that means the probability of win, win, win. So isn't that 0.038 on the, since they're independent, they're going to have the same probability for each play. So you win on the first, and you win on the second, and you win on the third. A more efficient way to write that is 0.38 to the 3rd power. And then we can get an approximate value. And I asked on this worksheet to round to 4 decimal places, so we will stick with that. Okay, that's part A. Part B says, suppose that the slot machine is played 5 times in a row. What is the probability of winning at least once? Okay, we worked on this yesterday, and I said when you see the words probability of at least one, that you need to automatically think 1 minus the probability of none. So we looked at this on the carabiner example. So if you go back to the carabiner example, that's what we first saw this. So I want to relate this rule to this problem. So this is something that's very helpful for us and important to use in a case like this. So we want the probability that we win at least once so that's the same as 1 minus the probability that we have no wins. Probability of winning at least once is the same as 1 minus the probability of none. None wins, no wins. 1 minus the probability of none, and none is related to wins. So that's why we're saying no wins. So I'm going to take 1 minus. Okay, now how many times are we playing? We're playing 5 in a row. Because it says, suppose the slot machine is played 5 times. I'll write it, what do they say? 5 times in a row. Okay, so if we're not winning at all, that's the probability of losing all 5. All 5 times you're losing, which is 1 minus. Okay, we were given up here in the original problem that the probability of winning is 0.038. Therefore, the probability of losing is opposite of that, right? It's the complement. So 1 minus 0.38 or 0.62, that's the probability of losing. I don't know why there's this weird, okay, there we go. There's a weird pink box right there. So the probability of losing is 0.62 based off of knowing that the probability of winning is 38%. So the probability of losing all 5 is your 0.62 to the 5th power. It's losing the first round, the second round, the third round, the fourth round, and the 5th round. And when you calculate that, we get approximately 0.9084. This is the most efficient way to solve this problem. If you did not solve it this way, it would be a lot of work. If you think about all of the outcomes of playing 5 times on the slot machine. So that would mean on a tree diagram, I'm not going to do this, but I'm just going to show you what that would look like or start to look like. Your first round would be win or lose. Your second round, if you win the first, you could win the second or lose the second. If you lost the first, you could win the second or lose the second. So this is only two times playing. You either win or lose. Given that you win, you either win or lose again. Given that you lose, you either win or lose again. Now I've got a third layer off of here because now I'm playing 3 times. So given what happened on the first couple rounds, now you have the 3rd round, then you have the 4th round. I'm not going to keep going on this, but you would fill all that out for the 4th round, and then it would be the 5th round. So you would have 5 layers of a tree diagram. All we calculated right here. Let me finish down here just to give you a little more perspective. Okay, all of those would have, okay, I'm not going to fill it all out, but you'd have 5 layers. So you would have first pull on the slot machine, you win or lose. Given that you win, then you have either win or lose. So this would be the 2nd pull. Then you have the 3rd pull, the 4th pull, and the 5th pull here. So what we calculated, what is the probability that we win at least once? So if I win at least once, that would be this first case, or this case, or this case, or this case, right? It would be all of these. because I'm winning at least once. Or it would be, if I win here, it would be all of those cases. Or if I win here, it would be all of those cases. Or here, all of those cases. Or here. So the only one that's left, the only option and the only way I could not win at least once is if I lost every single time. So I only would have to calculate this probability of lose, 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 lose versus all of these individual probabilities added together. That is why this is an excellent and efficient way to solve the problem. Okay, moving on. The next problem on the next page, this problem has to do with drag racing. A drag racer, this is number 6. A drag racer has 2 parachutes, a main and a backup. Okay, so there's a main and there's a backup. They are designated to bring the vehicle to a stop at the end of the run. Suppose that the main chute deploys with the probability, so the probability of 0.99, so that the main one will deploy. And if the main one fails to deploy, okay, so, let's just back up a little bit here. So if the main deploys, the probability will be 0.99, 99%. Or the probability will be only 1% if it fails to deploy. So I'm just using that as a complement. If it's 99% chance that the main chute will deploy, then I know there's a 1% chance it will fail to deploy. Erase this back upward so it give me a little more room. Okay, and then it says, suppose that the main chute deploys of 0.99 and if the main fails to deploy, the backup deploys with a probability of 0.98. Okay, so the backup has a probability of 0.98 of deploying. So that's the information I'm just getting from the paragraph. It doesn't hurt, and I encourage it strongly to write diagrams, write information before you just jump into the question. Part A on the question: what is the probability that one of the 2 parachutes deploys? Okay, I'm actually going to jump down to part B. So I want to do part B first because it just makes more sense to understand part B first. A is more clear after we do part B. I just need to switch this order on the worksheet and I forgot to. Okay, what is the probability that the backup parachute deploys? So the probability that the backup deploys. That's my question. Well, if I look above and my notes say, well, the backup deploys with a probability of 0.98. That's true, but what has to happen before the backup will deploy? Doesn't it make sense that first the main parachute has to fail and then the backup deploys? The main parachute has to fail first and then the backup deploys. So 0.98 is the probability that the backup will deploy, but the probability that the main will fail is 0.01. Oops, here it is. For the main parachute, the probability is 0.99 that it deploys, which means a 1% chance that it will fail. So it has to fail first in order for the backup to deploy. So that means I will just multiply these probabilities together. So the main parachute fails and the backup deploys. So we get an answer of approximately 0.9998. Oh no, I didn't do that right. Did not do that one right. I'm looking at a different answer. So if you multiply 0.01 times 0.98, we get 0.0098. Okay, so the main has to fail first, which is this very small probability that that's going to happen. Once that happens, then the backup deploys. So the probability that the backup deploys is going to be 0.0098. Let's go back up to part A. Part A says, what is the probability that one of the two parachutes deploys? So that means the main has to deploy, or the main fails and the backup deploys. So the probability that the main deploys is 0.98, or, so I'm adding that the main fails, which is 0.1, or 0.01, I got that backwards, 0.01, and then the backup deploys is 0.098. So 0.98 plus, we just calculated that right here for the second part. So 0.0098. And then when I add those together, I get 0.9998. Okay, so for this one, it was just easier to think about part B first, because we were able to use that idea in either the main deploys or the backup deploys. Okay, let's move on. Going on to number 7 now. Okay, so number 7. Microcircuit technology manufactures microcircuits that are used in computers. 12% of the circuits are defective. 12% are defective. That's all we know from the information in the first sentence. Assume that 3 circuits are installed in a computer. So we have 3 circuits. Denote a defective circuit by D and a non-defective circuit by N. List all of the outcomes in the sample space. So D is a defective circuit. N is a non-defective circuit. So if it's asking me for the sample space, there's only 3 circuits. I can draw a tree diagram. The first circuit is either defective or not defective. Given that the first circuit is defective, then the second circuit is either defective or not defective. Given that the first circuit is not defective, then the second circuit can either be defective or not defective. So right now I only have 2 layers. So I only have 2 options for 2 circuits. I have actually 4 options for 2 circuits, but 2 layers, which have 2 circuits. So the third option would be, given that I have defective first, defective second, then my third will either be defective or not defective. And I can continue in that same way with my tree. So in my tree, this is just the work that I use to come up with the sample space. The sample space is reading the tree. So DDD, DDN, DND, DNN. So DDD, DDN, DND, and DNN. Or NDD, NDN, NND, NNN. Okay, or we have NDD, NDN, NND, NNN. This is all of the possible options that 3 circuits can be ordered, defective and not defective. Part B. What is the probability that all 3 circuits are not defective? So the probability not defective, not defective, not defective. Okay, so I have to go back up here and remember what was given. And what was given is that 12%, it was given that 12% of circuits are defective. So the probability of defective is 0.12, which means the probability of not defective would just be 0.88, opposite of that, right? So I'm going to use that idea to figure out the probability that all 3 are not defective, which would be 0.88 is a chance that it's not defective, and it's to the 3rd power. Not defective, not defective, not defective. Okay, so we get that answer to be approximately 0.681. Part C says the computer will function so long as either 2 or 3 of the circuits are non-defective. What is the probability that a computer will function? So the probability that 2 or 3 are non-defective. So go back to your diagram that you drew to list the sample space, which is the tree diagram, and look at the sample space. We want 2 or 3 that are not defective. Okay, all 3 of them not defective, 2, 2, 2, that, right? Just those 4 cases. 2 or 3 are not defective. The other ones only have 1 not defective or none that are not defective. So the probability that 2 or 3 means the probability of 2 that are not defective, and let's see, or the probability that 3 are not defective. So the probability that 2 are not defective is going to be the case where we have DNN or NDN or NND. So are you seeing that these are just have 2 defectives in them? Those are all the cases with only 2 defective or 2 not defective. I'm not saying the right word. So those are the 3 ways that we can arrange 3 circuits where 2 of them are not defective. And then I need to add in this last one where all 3 are not defective. Last case here. So I need to compute each of these probabilities and add them together. Okay, so probability of defective is 0.12. Probability of not defective is 0.88. And I can write that twice because I have not defective, not defective. But I certainly can write this more efficiently with an exponent. Moving on to the next option where the first is not defective, then I have defective and then not defective. So not defective, defective, not defective. But again, I can write this in more efficient way because I can write that as 0.88 squared. And then the third way, not defective, 0.88, 0.88, and then defective 0.12, which I can write as 0.88 with the exponent of 2. I can always multiply in any order. So if I have 4 times 5, that's the same as 5 times 4. So I'm choosing to write my multiplication in this way because I'm leading you into chapter 6, but because I'm writing this as the defective part and then the not defective part. And then the last one we had just computed from up here. So 0.88 to the third power. So notice that all of those are the same. These first 3 are the same. So I could write that as 3 times. Instead of adding each of them, I can say 3 times 0.12 times 0.88 squared. And then I'm going to add in the last option of all 3 not being defective. So when I calculate this, I get approximately 0.9603. Okay, so the way I wrote that out really is leading you into the binomial distribution in 6.2. I'll just write that down so you have a reference. So you don't have to write it like I did here, but I am just helping you as you move forward into the next chapter. Okay, so these are all the ways that we can have 2 not defective or 3 not defective. We highlighted them up here, so I have to consider all of those options. The probability of each of these options. This option, this option, this option, this option. And then I calculate the probability of each, add them all together. And I'm just writing them in a more efficient way and getting my answer. Let's go on to part, let me know what part we're on. C, D, we're on D, part D. Okay, part D on this problem says, would it be unusual for all 3 circuits to be defective? Unusual for defective, defective, defective. So I need to find the probability of defective, defective, defective. So 0.12 to the third power, which is approximately 0.002. And right now in our class, we are measuring unusual with 5%. So if your probability is less than 5%, we consider it an unusual event. So since 0.002 is less than 5% or 0.05, then it is unusual to have 3 defective circuits. Is that probability small enough where it's unusual? So we consider a small probability less than 5%. Okay, let's keep going. Looks like we are on question number 8. Okay, question number 8. Just want to make sure I have enough time to get to some of the counting stuff. Okay, number 8. A 6-sided die has 1 face painted red. Okay, so 1 is red, 2 are white, and 3 faces are blue. Okay, so you imagine what a 6-sided die looks like. 1 side is red, 2 sides are white, and 3 of the sides are blue. Find the probability that a blue face turns up. So we also need to know that each face is equally likely to turn up when the dice is rolled. Okay, each face is equally likely, but it's less of a chance for me to get a red face than it would to get a blue face. Do you see that? Only 1 side is red. So if I roll the die, I only have 1 out of the 6 chances to get a red. I have 2 out of the 6 chances to get a white, and a 3 out of the 6 chances to get a blue. So the probability of a red is 1 out of 6. The probability of a white is 2 out of 6, or that reduces to 1/3. And the probability of getting one roll as a blue is 3 out of 6, or 1/2. So part A, find the probability that a blue face turns up. Part A is exactly 1/2. On one roll, the probability of getting a blue is 1/2, 3/6, or 1/2. Okay, part B, if we roll the die 3 times, what is the probability that each color turns up? And we want all the cases where we have one, we have a red, we have a blue, we have a white. But that's only one order, right? That would be red first, blue second, white third. There's other ways. So I need to think about maybe a tree diagram again. Let's do that. So your tree diagram, on your first roll, let me rewrite that. We're going to have 3 rows. So the first row, red, white, or blue. On the second roll, if you have a red first, your second roll is going to be red, white, or blue. If you have a white first, your second roll is going to be red, white, or blue. And the third roll, I'm going to make this longer so I have more room. If you have blue first, you have red, white, or blue. So that's only 2 rolls. So now I need to take and look at red, white, blue off of each of these. Red, white, blue. Red, white, blue. Getting squished here. Red, white, blue. Red, white, blue. Red, white, blue. This is why a tree diagram sometimes is a lot more challenging when you have so many options, because it's hard to draw it big enough. Okay, so those are the 3 layers, and we're trying to find out when we get one of each color. So if I start with red, then I don't want any more reds in my next rolls. So I can go red, white, and I'm going to write the cases out here. Red, white. Okay, so I don't want another red, I don't want another white, but I can go red, white, blue. Or I could start with red again. Whoops. I could start with red again, and this time I'm going to go blue. So if I have red and blue, I don't want to have another red. I don't want to have another blue. So I'd go red, blue, white, because we only want one of each color. So I'm just using the tree diagram to come up with the different combinations of getting one red, one white, one blue. How many ways can I arrange red, white, blue in different orders? Okay, so now if I start with white, white, red, I'm not going to grab red again. I'm not going to grab white, but I will grab blue. So my next option is white, red, blue. Okay, continue that. White, and then I don't want to do white again because I already grabbed white. So white and then blue. I don't want another white. I don't want another blue. So I'm going to have white, blue, red. Okay, and then my last options here are starting with blue, blue, then red, then white. So blue, red, white, or blue, white, and then red. Blue, white, and then red. I already have blue, so I would not even consider that next layer. So I came up with the 6 ways. Using a tree diagram, you might be able to just think about how many ways to arrange red, white, and blue, how many different ways, but here are the 6 ways. So I have 6 ways to arrange the red, the white, and the blue. Okay, so what is the probability of red? The probability of blue, and the probability of white. Well, we found out that with red, we have 1/6 of a probability. And we know that blue, there's 3 6 or 1/2. Probability of white is 2 6 or 1/3. So we want a red, we want a white, and we want a blue. And there are 6 ways to do that. Do you understand why I'm multiplying by 6? I know that if I come up to each of these probabilities, so this probability, red, white, blue, red is 1/6, white is 1/3, blue is 1/2. So that's the probability for red, white, blue. But isn't it the same probability for each of these, just multiplied in a different order? So red, blue, white would be the same as red is 1/6, white, blue is 1/2, white is 1/3. So it's the same, but just arranged in different orders. So all of these 6 options have the same 1/6 times 1/2 times 1/3, same multiplication, different order, but same multiplication. So since there's 6 of them, instead of adding those 6 together, I'm just going to multiply by that 6, more efficient. So when you do this, you get approximately, let's do it with just to be clear on the math. Multiply 6 across the numerator. So I multiply 6 all the way across the numerator, and then the denominator, because this is really like 6/1. 6 times 2 is 12 times 6, and I get 36, which is 1/6, or approximately, if I'm rounding, 0.1667. All right, let's now move into, I need to make sure I'm giving myself enough time and I'm getting close to this. Okay, I think I'm going to skip 9 and 10 on the worksheet because I want to go into something that I think students are struggling with more than these 2 problems. If you're confused about 9 or 10, then send me an email and we will definitely go over those together. Okay. I can just maybe take a picture, but I'll do that. Let's see if I can. Okay, I'll do it after. I'll do it after class to make sure I have time. I'll give you the answers if that's helpful, but I think I would rather just wait and see if you even need help. So how about you just wait? How about you just ask me if you need help like I originally had said? What I want to do now is I want to go into a problem that is on your homework, something similar to this. So this is in 5.5, and this has to do, I think you had like citations or something. So it was at a university, and there was, I think it was a problem about university has this committee that decides the citations that you get. And then they have this jury that decides whether you get the citation or not. So the jury is made up of 13 students and 7 faculty, and we're going to choose 5 from the 13 students and the 7 faculty to be on the jury for these citations. Okay, does that make sense? There's 13 students, 7 faculty, and we're going to randomly select 5. What is the probability that all of the jury is students? So I need to know, first of all, how many ways I can choose out of the 20. Okay, so there's 20 students. Out of the 20, what are all of the combinations? I can choose 5. That is the total number of ways I can choose 5 out of the 20. So out of the 13 students and 7 faculty, those are all of the ways I can choose 5 for the jury. I want the probability that all of them are students. So I want out of the 13 students, I want all 5 of them to be in the jury. Out of the 7 faculty, I want 0 of them to be in the jury. All students, so look what I did here. Out of the 13 students, I want all 5 of them to be on the jury. I don't want any 0 of the faculty. I'm not going to calculate these until we get these set up. Okay, so let's think about how that's different from here. So we still need to take this out of the total number of ways we can choose 5 for the jury. So 5 out of all of the 20, which is the students and faculty combined, how many ways we can choose that? That's the denominator. The numerator, if I'm looking at the students, there's 13 students. I don't want any students, but I want out of the 7 faculty, I want all 5 of them from the faculty. And this last one, out of the 20 people, I'm going to choose 5. I want 2 of them to be students. So a combination out of the 13, I want 2 to be students, and out of the 7 faculty, I want 3 of them to be chosen. So 2 students and 3 faculty. 2 out of the 13 for the students, 3 out of the 7 for faculty out of the total. 2 students and 3 faculty. It's a multiplication in the numerator. For all faculty, 0 students and 5 out of the faculty. For all students, all 5 out of the students and 0 out of the faculty. I'm going to come back to how to calculate that in a minute. Let's now look at this next example, which I have here. Okay, so this is, you don't have this worksheet. Let's look at this example though. It's not really a worksheet, it's just a problem. So you can write your notes on this. Let's look at this cracked eggs examples. So from this example, Alyssa collected 190 eggs from the chicken coop, and she finds that 25 eggs are cracked. If she randomly selects 8 eggs from the 190 and calculates each of the following probabilities. So what we know is we have 190 eggs. We have 25 that are cracked, which means, because if I take 190 and I subtract 25, I know I have left 165. So 165 are not cracked. Okay, so let's try to find the probability. And we're selecting 8. Okay, we know we're selecting 8 because it says right here, we're selecting 8. So select 8 eggs. We have 190 eggs. We have 25 that are cracked, which means I have 165 that are not cracked. So the very first thing I want to do is I want to know how many ways can I select 8 eggs. So the first thing is the combination out of the 190 eggs. I want to select 8. That's your denominator. That's the total number of ways we can select 8 eggs, whether they're cracked or not. So if you could think about how many ways that you have 190 eggs and how many ways you can select 8 and they can all be arranged. Okay, so now that's the denominator. So what is the probability? The first one is the eggs are not cracked. All are not cracked. The probability that all are not cracked, we'll call that part A. So I know out of the total combination 190, we're choosing 8. I'm going to set it up in the way where I'm going to look at cracked, not cracked. So out of the cracked ones, which there are 25, so 25 cracked ones, I want 0 of them to be cracked. Out of the 165 that are not cracked, I want all 8 of those to be not cracked. Okay, like I said, we will come back and do the calculation on these when we get these set up. Let's look at another example. So what is the probability that exactly 2 are cracked? Okay, probability that exactly 2 are cracked. So out of all the ways, 190 eggs, we're choosing 8. And I set this up as the cracked eggs first. So out of the 25 cracked, I only want 2 of them. Out of the 165 that are not cracked, how many are left? So if 2 are cracked and I'm choosing 8, 6 of them are not cracked. So that 6 comes from the 8 that I want minus the 2 that are cracked, gives me the 6 that are not cracked. Part C. Probability that exactly 5 are not cracked. So the probability exactly 5 are not cracked. Denominator is always the same because it's just the number of ways you can choose 8 out of the total number of eggs. Okay, the first one is the cracked egg. So out of 25, how many do we want cracked? Okay, we know we want 5 not cracked. So 8 minus 5 would be 3 that are cracked times combination of 165 that are not cracked, and I want 5. I want 5 of those. 5 that are not cracked. Just like we did here, 2 that are cracked. That 2 came from the cracked eggs, which left me the 6 for the not cracked. 5 are not cracked, which left me with 3 that are cracked. Okay, that's it. Okay, so that hopefully is helpful, especially with the jury one. Come back to the jury one. So let's now talk about how we calculate this. So you certainly know there's a formula. So the formula, if you've done 5.5, so if you haven't done 5.5, it's due today. So 5.5 for the combination, and they use n and r. So this is n factorial over r factorial times n minus r factorial. So if I wanted to calculate something like 20 choose 5, I would take 20 factorial, I would divide it by 5 factorial times 20 minus 5 factorial. This is by the formula. 20 factorial times 5 factorial. I need to subtract 20 minus 5 and get 15 factorial. And then I can calculate that. If you remember, when we talked about factorial, I can't remember what Zoom meeting it was, but it was early on. Factorial means you start at that integer and you multiply it all the way down until you get to 1. So 20 factorial is 20 times 19 times 18 times 17 times 16, all the way to 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 15 factorial would be 15 times 14 times 13 times 12 times all the way down to 1. This is a lot of work and a lot of tedious multiplication and drawing out that you don't need to do, but that's what a factorial, that's what that symbol represents. I'm not asking you to do that, but that's what that factorial represents. So just know that 20 factorial is a giant number. And if you try to put that in your calculator, by the way, check your charge on your calculator. Make sure your calculator is charged. I opened my calculator today and it said low battery. So make sure your calculator is charged on a side note. Okay, so 20 factorial. You would put 20 on your screen. So on your screen, put a 20, then hit your math button. And then arrow over to probability. And then you will see on number 4, so then arrow down to number 4 and you see the factorial. So you would press enter. And then on your screen, you would see the 20 factorial, press enter again. And we get 2.432902008 E18. You know to look at the very end of your calculation because this is that scientific notation. So the scientific notation 2.432902008, that E18 means times 10 to the 18th power, which means I would take this decimal place and move it 18 places to the right. But because you understand that factorial means to multiply 20 times 19 times 18 all the way down, if you wrote something like 2.4 on your paper for 20 factorial, that doesn't make sense because 20 times 19 times 18, that's going to be a huge number, not 2.4. So be very cautious of how you're reading your calculator, but you have to make sense of the answer as well. It doesn't make sense for 20 factorial if you wrote down 2.4. So this number, you could get that number, you could divide it by, we're trying to calculate this up here, just reminding you where we're going. We're trying to calculate this. So all I showed you right now is a 20 factorial. So we could do the same and divide it by that denominator. We can also, I'm taking a little bit more time on this. So you could in your calculator put 20 factorial, use your division, put parentheses because it's the whole denominator, put your 5 factorial, put your 15 factorial, and you can get your answer that way, making sure you put parentheses, and you'd have to just keep going in and grabbing this factorial option under math probability. So you could do that, or you could go back to, so if we want to compute combination of 20, choose 5, then go to math. You might have to put 20 on your screen. I usually always do first. So I put whatever I'm taking your sample size, so I'm putting that in value first. So put 20 on your screen, choose math, arrow to probability, and then you'll see on number 3, so arrow down to number 3, and it has NCR. Press enter. So on your screen, you'd have 20, you'd have C, and then you have this flashing cursor, and that's where you put your 5. So that flashing cursor, you would enter 5, and then you would press enter. And you get 15504. Okay, so a combination of 20 and you're selecting 5. So this is the jury one that we were looking at. So in the jury, we were selecting 5 out of the total 20. And all I did was calculate the denominator. So all of these have that denominator. So you're taking your fraction with the denominator of, we got our answer to be 1,504. So that's the denominator number. The numerator, so let's just do this first one, but we'll do the last one because I don't, probably just one example is enough. Okay, so I'm going to do this last one. So we know that right now we have 1,000 or 15,504 is my denominator. In the numerator, on your screen, put 13. So you're going to go 13. You're going to go to math, probability, grab number 3. So 13, math, probability, and then put in, then you'll have to put in, we're looking at 2. So on your screen, you would have 13C2, and then you could use your multiplication. So move your arrow key up, move that arrow key up, do your multiplication, and then put in 7. Go back to math, probability, grab number 3, put in your 3, and then press enter. And your answer is 2730. And then you can divide that by your denominator, which is approximately 0.1761. Okay, so that's how you use your calculator. I encourage you to use your calculator, but this whole thing that I did with all that multiplication out, that's for you to know and understand what your calculator is giving you. Your calculator, you should expect when you go to enter in 20 factorial, you should expect something a lot bigger than 2.4 because it is. You have that scientific notation times 10 to the 18. That decimal point is 18 places to the right. So it is a giant number. Okay, that is it. So that's your probability. 5.6 is the review on all of the probability methods. So keep practicing that. Go over the chapter 5 at the end of chapter review. That's not graded, but it is available for you to practice. Your exam is next week, and you have 2 sections of chapter 6 to learn. So make sure you get a really strong foundation of chapter 5, and maybe use this weekend to refresh on chapter 4 as well. All right, everybody, have a great night. Just turn in your notes. I'm not going to give you an extra assignment. That is good. And don't forget to do your reflection questions as always.